Accident prediction and timely warnings are vital for improving road safety and minimizing the loss of lives and property. Here we, Group SafeRoute Analytics, aim to help building advanced driver assistance system by improving performance of traffic accident anticipation systems and predicting time to the probable future accident while predicting future drivable area.
In this task, we are trying to solve those problems which are crucial for a successful advanced driver assistance system. Here we try to build an improved accident anticipation framework which is also capable of predicting time to probable accident along with a reliable future drivable area prediction system. In this task, we tried two paths to improve the graph framework. One is to improve feature engineering pipeline by introducing ego vehicle specially and also improving distance measures between objects. Other way is improving model architecture to capture and process more data. You can see some noticeable improvements in average precision, while there is no significant change in mean time to accident measure on DOTA and DADA datasets after improvements we done. Now let's move to some demonstration of the final system. Here you can see when accident is close, algorithm detects it. We have added a red tone to the video when model detects the accident. We predict accident timing using 5-second dashcam clips from the DOTA and DADA datasets, each sampled at 10 frames per second. Our graph framework extracts scene, object, and temporal features using a pre-trained i3D model and graph networks. We train 3 deep survival models, logistic hazard, deep hit single, and Cox time, using PyCox and PyTorch. Accidents are mapped to 50-frame intervals, non-accidents are right-censored at 5 seconds. We estimate collision time using a threshold method and expected time to collision, ETTC, enabling real-time, probabilistic accident prediction. Here's the result evaluation of our deep survival models. We assessed performance using 4 metrics: C-index, NBLL, Breyer score, and IBS across both the DOTA and DADA datasets. The logistic hazard model consistently outperformed others, achieving high C-index scores and the lowest error values, making it the most accurate and reliable. Deep hit single and Cox time also showed strong performance, while the random baseline lagged behind significantly. Visual survival curves confirm the model's ability to predict events early and accurately, demonstrating its strength in real-time accident forecasting. This segment shows how survival probability drops in real time during an accident. At first, conditions are safe, but a sudden U-turn at 1.7s triggers a steep decline. By 3s, a collision is nearly certain, and at 4.7s, the crash occurs, matching the model's near-zero survival prediction. Autonomous vehicles need accurate drivable area prediction to avoid collisions. We compared 2 key approaches: predicting future frames for later segmentation, and directly predicting future segmentations. Our method combines both strengths using a 2-step approach. First, we use SIM-VPV2 enhanced with gated spatio-temporal attention. It takes 10 RGB frames and predicts the next 10. The encoder compresses spatial details, the translator captures motion using attention, and the decoder reconstructs the future frames. We focus on the 4th predicted frame. Next, YOLACT++ performs real-time instance segmentation. It uses a RESNET50 with feature pyramid network to detect drivable areas and dynamic objects. This slide shows the evaluation results on the Cityscapes dataset using different segmentation methods. Although our model processes lower resolution frames, it outperforms earlier 2-step models such as X2X, highlighting the strength of our SIM-VP combined with the GSTA pipeline for frame prediction and segmentation. However, it falls short of surpassing the latest state-of-the-art techniques. This is a demonstration of predicting the next 10 frames using the past 10 frames with the SIM-VP GSTA model. Then, we feed the 4th predicted frame into the YOLACT++ object segmentation model, and these are the final results we obtained from our 2-step approach. With those results, we can say that there is a very much room for improvement in current accident anticipation systems, and also they lacks the ability to predict time to the accident. Our time to accident prediction system can be the solution for it. Furthermore, there is a potential in two-step drivable area prediction systems to become state-of-the-art frameworks in the area.